Hello everyone, my name is Arman and we are going to study Introduction to Probabilistic Combinatorics in this series of lectures. As you may know, Probabilistic Combinatorics is usually a graduate course, but my goal here is to explain the concepts in a simple language and include the prerequisites as much as possible to make this course self-contained and therefore usable by undergraduate students as well. As you know, combinatorics has different branches, and one important branch is graph theory. And we look at graph theory and in particular Ramsey theory in this course, and we'll see how to use probabilistic methods to derive important results in this field. So a very general idea here is that to prove the existence of a certain structure, we can define an appropriate probability space and show that a randomly chosen element of this space has the desired property with a positive probability, and that will prove the existence of the structure that we want. So I'm going to go into the details of these topics, Ramsey theory, probability theory, and probabilistic methods later. But first, let me tell you about the references that I'm going to follow more or less in this course. So let me share my screen with you here. Okay, so let me tell you about the references that you can use for this course. References. So I'll follow the lecture notes by Professor Reardon in Oxford University. So the name of the course is C8.4, Probabilistic Combinatorics by Professor Reardon, Oxford University. Okay, and the other book that you can use is the very standard book in this field, which is entitled The Probabilistic Method by Allen and Spencer. This is published by Wiley. Okay, so let's get started. So we'll start with graphs. So I'm sure you're familiar with graphs and like the important properties or basic features of graphs, but let's do a quick review about this, and then we'll go to Ramsey theory in particular. So graphs. Okay, let's start with the definition of a graph. Definition. Okay. In this course now we want to work with finite graphs. So in general, graph could have infinite number of vertices, but here in our context we work with finite graphs. So let me say that let V be a finite set and E be a set of two sets of elements of V then G equals V and E is called a graph. The elements of V are called the vertices of G, and the elements of E are called the edges. The edges of G. Okay, so for example, let V equals V1, V2, V3, V4, and E equals, let's say, V1, V2, V1, V3, and V2, V4. Okay, so this is a, then G equals V and E is the following graph. So a graph with 4 vertices. So let's say V1, V2, V3, V4. Okay, 4 vertices. And V1, V2. So let me call them V1, V2, V3, V4. Now V1, V2 is an edge. V1, V3 is also an edge. And V2, V4 is an edge. So here V1, V2, for example, are adjacent because there is an edge between them. But V3, V4 are not adjacent because there is no edge between them. Okay, so see, V3 and V4 are not adjacent, but they are connected, meaning that yes, there is no direct edge between them, but still we can go from V3 to V4 via another path, which will be V3 to V1, then V1 to V2, and V2 to V4. So another concept, important concept in graph theory is path and also connected graphs. So definition, a sequence of distinct edges in a graph G is called a path. Okay, and the next definition, the vertices Vi and Vj are called connected if there is a path starting from Vi ending in Vj. And the next definition, a graph G is called connected. It's called connected if any two vertices of G, are connected. If any two vertices of G are connected, then we call the graph to be a connected graph. Okay, so in example above, note the graph given in example above is in fact connected. Why is this connected? The graph that we showed in this example, look at this example. Well, V1 and V2 obviously are connected because there's edge between them. They're adjacent, more than being connected. And V1, V3 is similar, V2, V4 similar. V3, V4 are not adjacent, but there is a path between them. So any two, or also, V1, V4. So any V1, V4, again, they are not adjacent, but they're connected. So any two vertices that we consider in this graph are connected. So we call the graph connected. Okay, now another definition that we need, complete graph. Complete graph graph with n vertices is called complete, and is denoted by Kn if for any two vertices of this graph there is an edge between them. So complete graph is a graph where it has all possible edges. Okay, the next definition is induced subgraph. So let's give this definition. Let G equals V and E be a graph. And let S be a subset of V. The induced subgraph. So notation is G of S is the graph whose set of vertices is S and whose edge set consists of all the elements of all the edges in E that have both endpoints in S. Okay, so in order to have a subgraph, first we need a subset of V, and then we consider all edges corresponding to that subset. When I say corresponding means, so both endpoints of the edges have to be in S. So if one endpoint is in S, one endpoint is not in S, then we do not consider that edge. So only edges that both endpoints are in S. So we get a new graph. The set of vertices is S. And we have also a new set of edges. We have a new graph. So that new graph is called induced subgraph. And G of S is the notation. So let's look at an example. Let's say if you have, let's say this graph here. So let's call this one 1, 2, 3, 4, 5, and 6. So let's say if S is equal to 1, 2, 3, okay. Now this one is G, and then G of S is, so we have three vertices, 1, 2, and 3. Okay, so this is 1, 2, and 3. And I have to consider only the edges where both endpoints are in S. So this is one of them. This is one of them, right? 1, 2, 3. But for example, this one is not an edge in the new graph because one endpoint is 2 is in S, but one endpoint 5 is not in S. Similarly, this one is also not. So I have to delete them. So this is G of S. Okay, Now, next definition is clique. Definition, again, let G equals V and E be a graph. A clique of size, let's say R, is a set, I can say a subset of V such that any two vertices in this subset are adjacent to each other. In other words, induced subgraph of this set with size R is KR, the complete graph KR. So basically, intuitively, if you have a complete graph inside a bigger graph, well, that complete graph inside the bigger graph is called clique. If the complete graph is KR, then it will be called clique of size R. So we usually mention the size of clique as well. Okay, so again, an example. Let's say if I have this graph here, then here. Okay, so it's a 1, 2, 3, 4, 5. Okay, so what is clique here? So clique is a complete graph inside another graph. So I have a triangle here, which is a complete graph of size 3. So S equals 1, 2, 3 here is a complete, is a clique of size 3. Is a clique of size 3. Okay. All right. So another concept similar to this, but actually opposite of this concept, is independent set. So definition, an independent set in a graph G equals V and E is a subset of V such that there is no edge between any two elements of this set. An independent set is also called anti-clique. This is opposite of clique, right? For clique, it's complete graph. You have edges between any two vertices. Here, you do not have any edge between any two vertices. So, for example, Okay, before doing the example, an independent set of the maximum size in a graph G equals V and E is called the independence number of G. All right, so let's look at an example. Let's say we have this graph here. 1, 2, 3, 4. And again, this graph. Let's say this one here. 1, 2, 3, 4, 5, 6. So which set is independent set here? So for example, if I say 5 and 1, or there is no edge between 5 and 1, so that's okay. And if I add 6, for example, still it will be independent, right? So 1 s equals 1, 5, 6. So there's no edge between 1 and 5, no edge between 1 and 6, no edge between 5 and 6. But I cannot add 2 to this because 1 and 2 there is edge. I cannot add 3, I cannot add 4 similarly, right? So this is an independent set. Set in G. This is my G, let's say. Okay, so you know that these graphs have lots of applications. One simple application is that you can consider the vertices as being people, and edges could represent friendship between people. So if, let's say, two people are friends, there is an edge between them, and if they are not friends, then there is no edge between them. Well, but let's say if you want to still categorize the friendships, for example, let's say, well, we know that if two people are friends, there is edge between them. But let's say if you want to know whether, when we say they're friends, okay, are they friends how did they become friends, for example? Did they become friends from in school, or let's say in work, or neither work nor school? So let's say, for example, if you want to categorize into 3 categories. So how did they become friends? In school, work, or neither? So we want to categorize the edges. So in this type of situation, we will label the edges. So edge shows friendship, but then I can label it as, for example, 1 or 2 or 3. 1 means that they became friends in school. 2 means they became friends in work. 3 means they became friends neither in school nor work. Okay, so sometimes we need labeling. So let's give the next definition. A vertex labeled graph is a graph G equals V and E together with a function from V to a set of labels. Now, if you want to label, you can use numbers, label number 1, label number 2, or we can use also colors. In Ramsey theory, we usually use colors, red, blue, or other colors. Similarly, an edge labeled graph is a graph G equals V and E together with a function from E to a set of labels. Okay, note in this course, by labeled graph, we mean edge labeled graph, and we use colors to label the edges. Okay. So for example, let's say I have 4 vertices here again, and let's say this one I use red, and this one also red, and then this one I use blue. Okay, so this is an edge labeled graph with 2 colors. Okay, so now we are ready to start Ramsey theory. Okay, let me start with a very simple example. Let's say we want to consider a card game with 3 participants, and in this game it is important whether participants know each other. Let me say whether participants have played with each other before or not. Okay, this makes sense, right? If 2 people have played with each other, let's say in a card game, they somehow know their tricks that they're going to use in the game, right? And so the situation will be different compared to when 2 people haven't played with each other and they don't know what type of tricks they use in this card game. So this means that to have a fair game, right? To have a fair game, we want to run a game where any 2 of 3 participants have played with each other before or any two of three participants have not played with each other before. Okay, so if we have, let's say, three participants, two of them have played with each other before, but the third participant have not played with any of those two, well, that's not fair, right? Because the ones that have played with each other, they know their tricks somehow. Okay, so now let's say you want to, this is a game and this is the situation for having a fair game with three people. Now question is, in a party, how many people should we invite to ensure we can run the game described above fairly? At least, of course, how many people? At least how many people should we invite so that we can be sure that we can have either three people where any two of them are friends, or three people where any two of them are not friends, where friend here means they have played with each other before. Okay, so how many people do you think we have to at least invite? So we can formulate this easily in a language of graphs, right? So mathematically, we label or color basically the edges of a complete graph. So we color red if two people have not played before, and color blue if they have played before. Okay, so the question is this question in red, blue, labeled complete graph Kn. We want to have a red click of size 3 or a blue click of size 3. What is the minimum value of n? So we will have a red click of size 3 if we have 3 people, or any 2 of them have not played before, and blue click of size 3 if we have 3 people where any 2 of them have played before. So what is the minimum value of n? The number of people that we have to invite, because when we invite people, we don't know whether they have played with each other or not. We don't ask them when we invite them. Okay, so first of all, I want to claim that this n, the claim n is equal to 6 is the minimum number of people that we have to invite. So first of all, I have to verify 2 things. That once I invite 6 people, I will have this condition. And another thing, in order to show that this is the minimum number, I have to say that if I invite 5 people, it's possible that what I want does not happen. Okay, so first, to prove the claim, first prove in red, blue, in any, it is in any red, blue coloring of K6, there is either a red click of size 3 or a blue size 3. So fix a vertex, say V1, okay, in V, which has 6 elements. These are my K6 is basically V and E. Okay, how many edges are connected to V1? Because I'm talking about a complete graph, right? So complete graph means any 2 vertices are adjacent. So we have all possible edges. So there are 5 edges connected to V1. So there are 5 edges connected to V1. Okay, so what I want to say, so there are 5 edges and we have only 2 colors, red and blue. So by pigeonhole principle, at least 3 of them have same color, right? So pigeonhole principle tells me that at least 3 of these edges have same color, say blue. I have 2 colors, 5 edges. So at least 3 of them have same color. So let's say it's blue. If it's red, again, similar argument, of course, holds. Okay, so see, I have V1 here. So let's call the endpoint of these edges. As, let's say VI, VJ, VK. Okay, so see, I have V1 here, and I have 3 blue edges here. So V, I, V, J, V, Okay, at least 3, same color which I assumed is blue. So I have 3 blue, at least 3 blue here. It could be more. Okay, so see, I have this situation here, Vi, Vj, Vk. Now I'm going to consider, again, remember we have all possible edges and each edge is either red or blue. So now I'm going to consider the edges. So consider the edges Vi, Vj, Vi, Vk, and Vj, Vk. So these 3 edges. So if at least one of these 3 are blue, then we are done. We have a blue triangle, right? So if at least one of these edges is blue, then we get blue clique of size 3. Size. Okay, is it obvious? Because see, I have V1 here, Vi, Vj. Now, if for example Vi, Vj is also blue, well, there you are. Then I have my blue triangle, which is clique of size 3. Similar, if Vi, Vk is blue, I'm done. And if Vj, Vk is blue, I'm done. Okay, so that's it. And what happens if this is not the case? If at least one of them is blue, then we are done. If this is not the case, then that means all 3 of them have to be red. So if not, all edges Vi, Vj, Vk, Vj, Vk have to be red. And in this case, we get a red clique of size 3. Okay, so we proved that no matter how you color the K6, you always have either a red clique of size 3 or blue clique of size 3. Which means once you invite 6 people, doesn't matter, you don't need to ask them whether they have played with each other or no. So there's always either 3 of them who, any 2 of them have played with each other before, or 3 of them where none of them, no 2 of them have played with each other before. Okay, to complete the proof of claim, we present a red-blue coloring of K6 that has no monochromatic clique of size 3. Okay, so previous case we had monochromatic. Monochromatic means single color, so either red clique of size 3 or blue clique of size 3. When we consider K6. But here, if I consider say K5, okay, for K6 we proved they always exist, but for K5, we present a red-blue coloring of K5 that has no monochromatic clique of size 3. So that means to ensure we have 3 people where any two of them are friends or any two of them are not friends, we need to invite 6 people at least. Because if you invite 5 people, there is a possibility that this does not happen. Okay, so what is the red-blue coloring of K5 that we're talking about? So it's going to be very simple coloring. So it's okay, and then all diagonals will be blue. Okay, so here, as you can see, there is no monochromatic triangle. There is no triangle of a single color. There is no red triangle and there is no blue triangle either. Okay. All right, so this is basically the concept of Ramsey numbers. So again, we can consider for higher numbers. Let's say you want to play a game with, let's say, 6 people. And again, you want that any 2 of those 6 people to be friends or any 2 of them not be friends. How many people should we invite to ensure this happens? For 3 people, we know we have to invite 6 people. But if the game, because the game was consisting of 3 players, but what about if the game consists of 6 players? How many people should I invite in total to be sure that I have 6 people where any 2 of them are friends or any 2 of them not friends? In the language of graphs, what n should I use to be sure that I have either a red clique of size 6 or blue clique of size 6? Okay, so these are called Ramsey numbers. So let me give the formal definition for Ramsey number to you. So definition, let R and S be positive integers. The Ramsey number capital R of R and S is defined as the least positive integer n with the property that every red blue coloring, red blue edge coloring of Kn contains either a red clique of size R or a blue clique of size S. Okay, so what have we shown above in the example we just proved? So note in above example, we proved that R of 3 and 3 is equal to 6. In order to ensure that we have either a 3 red click of size 3 or blue click of size 3, we need to have at least 6 vertices in total. We need to consider K6 because for K5 we saw that it may not work, but in K6 we proved that it works. Okay, so now this was Rn3, Rns both equal to 3, and it was a simple case. But what about if R and S are large numbers? So first of all, the first question we could ask, can we be sure that such number exists? Let's say if R is 100 and S is 200, can we be sure that there exists a Kn, there exists an n such that for that n, any red-blue coloring of Kn has either a red click of size 100 or blue click of size 200? The answer is yes, and this is exactly what Ramsey proved, and it's called Ramsey theorem. So Ramsey theorem, existence of these numbers, these Ramsey numbers, is proved by Ramsey. The Ramsey theorem for any positive integers R and S, capital R of R and S as defined above, exists and is finite. And is finite. Moreover, capital R of R and S is less than or equal to R plus S minus 2, choose R minus 1. Okay, so not only Ramsey proved that capital R of R and S exists and is finite for any R and S, he also provided an upper bound. He also provided an upper bound for these numbers R and capital R of R and S. So one of the main goals and one of the main mysteries of Ramsey theory is finding upper bounds and lower bounds for these Ramsey numbers R of R and S, which is still open problem. So I will show you that proving these bounds is rather simple, which gives some upper bound. We'll also derive lower bound, but none of these bounds have been significantly improved since then. Okay, so we'll see that they actually upper bounds and lower bounds are both exponential functions. So the behavior of these Ramsey numbers are exponential functions, but the base of the exponential function, that's what is still unknown, and it's the mystery. Okay, so let's try to prove this theorem first. So to prove this theorem, we first following lemma. For any positive integer R and S, we have just R and S, we have capital R of R and S less than or equal to capital R of R minus 1 and S plus capital R of R and S minus 1. But of course here, because R minus 1 and S minus 1 are appeared here, well then of course we need them to be greater than or equal to 2 so that both sides are well defined. Okay, so yeah, I think for first lecture, this much is enough. So I'm going to continue by proving this lemma and going to covering more details about Ramsey theory and upper bounds and lower bounds next time. And we also will develop the basics of probability theory, the tools we need from probability theory to derive bounds. Okay, so thank you and see you next time.